Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we are excited to have Fernando Brando visiting the Quark group. He's a candidate for a research position in Quark. And Fernando is from actually Brazil, hails from Brazil. And he obtained his PhD in physics from Imperial College London. Currently, he's an associate professor or lecturer at University College London, where you've been for about a year, I think. He's held positions at ETH Zurich, Universidad Federal de Minas Gerais. Oh, shoot, I speak French and not Spanish or Portuguese. And also University College London, Imperial College London. He's interested in quantum information theory, quantum computation, optimization theory, many-body physics, computational complexity, and entanglement, which is what we're going to hear about today. So he's going to talk to us about the complexity of quantum entanglement. Let's welcome Fernando.
Thank you. Thanks. So thanks for the invitation to come. I'm happy to be here and to interact with you during these 2 days. Okay, so I'm going to talk about some work that I did in collaboration with several people. Here are their names, and like over 3 or 4 papers. So the beginning, I was not sure what the audience would be, so I put some like very basic like motivation for doing quantum computation and so on. I don't think it's necessary here, but let me go really quickly over it, right? So how, the reason why we are doing what we do is if we consider 2 different problems, right? One is this problem of simulating quantum mechanical systems, right? So this is some plot that I took from a talk by Asper Guzik that many people use it now. It just shows that the time of supercomputer power from the Department of Energy in terms of the disciplines, right? And then you can see that like roughly 25% of this supercomputer power is devoted to simulate quantum physics, right? So this is a very time-costing simulation problem, and we would like to get a better handle on this problem, right? So another challenge is that we have cryptography, right? This works very well, but it's all based on unproven hardness assumptions, right? On computational hardness of given problems that we don't know for sure if they are hard or not, right? And of course, it will be much better if you can base security on more firm grounds, right? On, for example, the laws of physics, for example. And what quantum information and quantum computation gives is really a pathway for solving both problems, right? So if you want, one day we can build a quantum computer or like long-scale quantum cryptography systems, we can get much better answers for these 2 problems. So the area of quantum information theory, really the goal is to try to lay down a theory for these future quantum-based technologies, quantum computation, quantum cryptography, and so on. And there is a lot of sub areas, right, that we explore here, and you guys work on many of them here. So like in quantum communication, we understand the ultimate limits of information transmission, right? So we have quantum mechanical systems, and therefore we have to understand how we can store and manipulate and send information in these systems. Then entanglement theory, we see this quantum correlations entanglement that will be the focus of this talk as some resource in quantum information science. We want to understand how to use this resource. Then quantum error correction and fault tolerance is really about this idea that these quantum computers, they are actually in a sense digital computers, right? We have a meaningful way of correcting errors and scaling them up. Then in quantum computation, try to find ways of using a quantum computer once we have one, right? Trying to get algorithms with exponential speed up. And quantum complexity theory just comes from the idea that once we know the fundamental limits for computation due to quantum mechanics, we understand what are the limits for quantum computation, right? So what we cannot do even with a quantum computer. So there's a lot of work in all these directions, right? And they're all very interesting, but I guess a bonus of all this theory is that all this theory developed, it's not only useful for trying to understand what we can do with these new technologies, but also for studying other problems in other areas of physics and in computer science, right? And one of this will be one of the focus of the talk, right? So there is a lot of like emerging connections of quantum information theory with other branches of science. So I just put some like random examples here, right? So in condensed matter, there is a lot of stuff going on between strongly correlated systems and entanglement theory or topological order and quantum error correction. As you know very well, in high energy physics and general relativity, there is some very nice recent connections as well. What I want to focus here is on connections of our field, quantum information, with theoretical computer science, right? And in particular to optimization, okay? So there's been some works on, like, for example, understanding compressed sensing better using quantum information ideas. What I want to focus is to try to understand this very useful algorithmic techniques known as SDP hierarchies in terms of quantum information ideas, okay? So, but we'll get to that soon. Okay, so this talk is really just to give an example of these connections of quantum information theory with optimization theory in particular, and semi-definite programming. So the problem that we want to address from like a pure mathematical point of view is a very basic one. So it's just like a relation of quadratic versus biquadratic optimization. So let's start with some problem, which is completely elementary, right? This is just, we're given a matrix, Hermitian matrix, for example, d by d, and we want to compute this, the maximum over unit vectors of x transpose conjugate mx, right? So this will be the expression. So it's just a quadratic optimization problem in the entries of x. And of course, this is a very easy problem, right? This is just the maximum eigenvalue of m, right? So we just use linear algebra and we can compute this very efficiently and we understand it very well. Now let's try to generalize this problem a little bit, right? Just add another variable y. So now we have a m, again it's a Hermitian matrix, but it's on a tensor product of two vector spaces, one d-dimensional, the other l-dimensional. And now we want to solve the analogous problem, but instead of optimize over any vector, we want to optimize over product vectors, right? So x tensor y, where both are unit vectors, okay? So this is just like a general biquadratic optimization problem in x and y, right? So over some homogeneous polynomial, and we want to calculate the maximum of this, okay? Now it turns out that this is a much harder problem now. So we don't really understand very well the complexity of this problem anymore. But using some ideas from quantum information theory, we can both get the best known algorithm that we know for this problem and the best hardness result as well. And this is what I want to show you, okay? So just interrupt me at any point if you have questions during the talk. All right. Yes. Yes, please.
What's really the difference between the two problems?
Oh, okay. So
why cannot we just consider x tensor y to be a vector in?
No, you can. It's definitely a vector, but here you optimize over all vectors in the space. Here you only optimize over product vectors, right? We also have vectors which are not products, right? So that's why, yeah.
Another way to look at it is H is a tensor.
Yeah.
That's right. Okay, and
Quantitative.
so the way that these problems will appear in the context of quantum information is trying to solve a computational problem that people study a lot in quantum information, which is problem of detecting entanglement. Okay, so well, I guess I'll just you all know that. So a pure state is just a vector, right? In a d-dimensional complex vector space. We also care about mixed states. So these are just positive semidefinite matrix of unit traces, right? So positive semidefinite unit trace. We can always write as a convex combination of pure states if we want. Okay, and quantum measurement is just some POVM element. So let me just skip this. Now this is the point. So we want to understand when a quantum state is entangled or not, right? So we assume that we have a bipartite quantum state. Suppose it's a pure state, for example. So it's just a state on the tensor product of a d-dimensional versus a l-dimensional complex vector space. And now the way that we define entanglement is first to say what's not entangled, right? So we say that a state is not entangled if it's is a tensor product of two local states, a state on A, tensor state on phi. Then we say it's separable, and separable means it's not entangled, okay? So if you do a measurement on A, this is completely independent of the state on B, right? Or of whatever measurement you do on B. Now for mixed states, we have to, we're also interested in understanding when a mixed state when a mixed state quantum state is entangled. So here we are given a density matrix, right? So this is just a set of density matrices on this vector space. And now again, we define what are non-entangled states first. They are just convex combinations of product states. Okay, so just take our definition of non-entangled states in the pure state case, and we extend to mixed states by convexity. And otherwise, if you cannot find the probability distribution pi and product states psi I, phi I, such that we can write the state in this form, then we say it's entangled. It has like quantum correlations. Okay? Yes?
The quadratic problem you showed on the previous slide, is that considered in other fields? Is there other applications?
Yes. So I'll get to that in the end of the talk. Yes.
Okay.
Yeah. Yeah. All right. So now why make sense to define entanglement in this way, right? So this comes from considering this paradigm that we have in quantum communication and like cryptography, which is this LOCC paradigm. So this is the situation where we have two parties, Alice and Bob, and they are far away, right? They have like quantum labs. They can do whatever operation allowed by quantum mechanics locally, but they can only communicate classical bits to each other, right? So they are very far away. To send quantum particles is very expensive. They can only talk on a telephone line. So now they would like, initially they have no correlations, right? They didn't interact with each other. Now they would like to create a quantum state using this class of operations, local quantum operations and classical communication. This consists like Alice makes a measurement, sends some message to Bob, classical message. Bob makes another measurement, sends a message back to Alice, back and forth.
Well, the tensor product is the tensor product between Alice and Bob.
Exactly. Yeah. Right. So now the Hilbert space is given by a tensor product of vector space of Alice, tensor vector space for Bob. Now separable states are exactly these states which we can create by this class of operations, right? So they can just share like some coin given by the probability distribution pi. They just sample from this coin. If they get outcome I, Alice prepares the state psi I locally, and Bob prepares the state phi I locally. Okay, so it's clear that any states of this form can be created by just like classical coordination, and it turns out that any state that cannot be written in this form requires some kind of quantum interaction, right? So therefore, there must be some quantum correlations there. So entangled states is just states that cannot be created by LOCC. They have these non-classical correlations. Okay. So now we get to this computational problem that I would like to study in this talk. And the computational problem is the following. We are given a density matrix, right? It's just this PST, positive semidefinite matrix of unit trace. And we want to know if it's entangled or not, right? If it corresponds to an entangled state or to a separable state. So now it's useful to allow some error in the answer, right? Some accuracy for the problem. So we use this weak membership formulation. So it's easy to see that the set of separable states is a convex set, right? It's this set over here. D is the set of all density matrices. And now this weak membership problem is the following. So it's a decision problem, and we are given a state rho AB, and we want to determine if it's separable, if it's inside here, the set, or if it's epsilon away from separable, okay? If it's outside here. So it's really, there is no separable state close by. And of course, we have to use some norm to quantify, right, this epsilon, and we'll get to that soon. Okay, so it's just some version of deciding entanglement where we don't care what happens here when in this boundary here. All right, and now what we want to understand is how efficient we can actually solve this problem. There's also the dual problem, right? It's an optimization problem, it's a weak membership problem, so there is the optimization version of the problem. And this is really just when you optimize over elements in this convex set, right? Which is a set of separable states. And here you can see that this function that I mentioned before appears, right? So this HSEP is called like the support function at this point M of the set of separable states. The definition is just the maximum over separable states of this linear function, trace M sigma, right? M is just whatever matrix, right? It's a fixed matrix on this bipartite vector space. And then, right, of course, these are separable states. We know they are convex combination of product states. And we are taking a maximum over a convex set. So the optimal solution is in the extremal points, which are just product states. So we have exactly this biquadratic optimization problem. Okay? So the problem of deciding entanglement is tightly connected to this biquadratic optimization problem. One is like the dual of the other. If you have a good algorithm for one, you can convert it to a good algorithm for the other. But I'll get to that more later.
Is the trace is somehow interpreted as a distance between M and sigma?
The trace?
Yes.
No, this is just the trace of the matrix given by the product of the two.
Right.
Yeah. So
why are you maximizing that? What's
no. So this problem is just that you have this convex set, and you just wanna maximize a linear function over elements of the set. Okay. This is the definition of this problem. Now there are well-known results in like convex optimization, which says that if you can solve this problem, you can solve the weak membership problem as well, and vice versa.
Okay.
So the ability of solving one gives you the ability of solving the other, right? So when we study this problem, we can study this in place of it and vice versa.
To what extent is that notion of being separable and not stable under a discretization of our numbers? So if I work, instead of with reals, I work with floats, or I work with...
Right, yeah, it's a good question. And
could it make or break the fact that it's entangled or not?
so, yeah, so there might be some decomposition in terms of product states, which you cannot write if you only have, right, so like some fixed accuracy in the elements, right, of your matrix. Right, so, but that's why we allow for this error, right? Because with this error, then it's fine.
That will take care of all these numerical issues?
Yes,
Okay.
it will, yeah.
Epsilon.
Yeah.
That's what I'm worried about. That's what I'm worried about. If I make epsilon very small, can I still decide? Does it affect the...
No, you know, if epsilon starts being, I don't know, like exponentially small in the dimension or something, right?
10 to the minus 5
Yeah.
or something like that.
So, I don't know for this. So, you know, you just, it's a good question. I don't know, like given the fixed error, what the accuracy you need from the all the elements of the matrix such that it doesn't make a difference, right? So actually, I don't know. I have to think about it.
We can, of course, not work with the reals.
Yeah, that's true. Yeah.
Well, it might have something to do with the condition of Berlin.
Right. Yeah. But so what I have in mind here is just that.
I mean, how elliptical is that set? If it's really skinny, you know. You might,
Yeah. Yeah. So here we'll be most interested in constant epsilon, okay, and then we just can take all the numerical errors much smaller than that. So, and the relevance for this, right, is just what I mentioned before. Entanglement is this resource in quantum information science, like for cryptography or quantum communication and so on. So usually, you know, when someone builds up some experiment for doing something useful, the first test they should do is just to tell if there is entanglement or not there, right? Then they should characterize it further, but this is the, like, in a sense, a minimum requirement. So because of this, a lot of people study this problem, like in the past 15 years since like the beginning of quantum information, and now what I want to show you some results on this. So, but now before I get to the results, there is this norm here, right? So there is how we quantify the distance between two density matrices, right? And there are several ways of doing that, and it turns out that this is important for us, right? How we quantify this. So let me just show you some options. So this is how we quantify the distance in the weak membership. A nice geometric way, but not the most operational one, is using Hilbert-Schmidt norm. This is just the Euclidean norm for, you know, if you treat the quantum state as a vector, right? So this is this norm. It's just trace x dagger x to the 1/2. A more operational motivated version is what we call this trace norm. This is the mathematical definition, but it's useful one because if you look to the trace norm of the difference of two quantum states, then this is equal to 2 times the maximum over measurements, quantum measurements of trace m rho minus sigma, right? So this is just a P of m element, and we look at trace m rho minus sigma. So really this tells us the distinguishability of rho and sigma. If this is small, doesn't matter what experiment you do on rho or on sigma, they will have similar outcomes, okay? So for all practical purposes, if the trace norm is small, the two states, they are the same. Now, from thinking about this distant lab paradigm of having Alice and Bob and they can only operate locally, there is another operation motivated norm that we can think of, and this will turn out to be very useful here, which is we call the LHC norm. Okay? So this is the norm which tells the distinguishability of two quantum states under only local operations in classical communication. Right? So we have a restriction on the kind of operation of measurements that we can implement, and this just represents this restriction. So I consider a particular simple set of LHC, which is what we can say something about, which is called one-way LHC. This is very simple. Alice makes a measurement, gets some outcome, communicate the outcome to Bob, and then Bob makes another measurement condition on this outcome. And then they can implement some measurements in this way. So that's the definition. It's exactly like the trace norm, but M is not any measurement. It's just a measurement that you can implement by one-way LHC. And because there is like only forward communication from Alice to Bob, actually there is a nice characterization, but we won't need that, so don't worry about this. This is just a mathematical way of writing, but it's just like a sum of positive operators here on Alice and Bob with some normalization. This doesn't matter.
What's about this one?
This one reflects the fact that we only allow communication, classical communication, from Alice to Bob, and not the other way, and not like back and forth. We could also consider this norm where there is as many rounds of communication as we want, but the results will be more about this norm.
So if there would be two, what difference?
Then here this will be more complicated. So then you will have to have a recursive definition. Like you define for one, and for two would be like this one, and then there's another measurement here with this gets extremely messy, like the LCC. For example, it has just been proved it's not even a closed set. Okay, so this back and forth can complicate things a lot.
Thank you.
All right, so
N
yes.
LOCC and
Yes.
then run N all the way to infinity. Would
Yes.
you be able to approximate all the measurements there are?
No, so there are definitely measurements that can only be done non-locally, right?
Okay.
Even like with many rounds of communication. For example, measuring in a Bell basis, right? So you measure like in the base of maximally entangled states. This cannot be done by LCC, not even approximated by
I see.
LCC. All right, so the question is, tell whether rho is entangled, right? There's this weak membership problem. As I said, there's a lot of theory behind it. There's like these concepts of PPT states, entanglement witnesses. They're all developed to try to solve this problem. But once you turn this into worst case analysis for algorithms, they are not very interesting. So they only give like pretty bad algorithms. So I'll denote the local dimensions of A by this and of B by this. So they give like roughly exponential time algorithms only, okay, in the local dimensions.
What is the worst case? Is that important?
No, we don't understand the average case of separability. We don't have much results. Yeah, but we do know it's very costly even on practice. Okay, so it's not that there is some pathological cases and for most cases it's very easy. We do know that it usually it's very hard to tell whether I say it's entangled or not. Okay, and the same for HSEP. Okay, so we don't know. We had this kind of bound, and this is no better than just doing exhaustive search. All right, so we also understand why this problem is hard, right? It turns out that it's a computational hard problem for some parameters of the error. Okay, so this starts from a result by Gurvitz, and then many people work on that. You can prove that the problem is NP hard when the error is pretty small. It's like polynomially small in their local dimensions. And then this works for any norm you want, either one norm which is strong or two norm. It's always NP hard. Even like if you care about, this is for very small error, right? Even for constant error, there was a hardness result. It's more difficult to state, but let me try. So this just says that if you look at this time complexity, right? So it's exponential, some constant, log of A, log of B, up to some small corrections. This is like sub-exponential, right? So quasi-polynomial time. So it shows that under some assumption that I will tell you, there is no algorithm of this complexity. Okay, even when the error is constant, it's like 0.01. And this for any such numbers bigger than 0. Okay, I'm being very specific because this will be an important function in the following. So it seems that there is this limits of getting an algorithm of like faster than exponential in log dimension of A, log dimension of B. And the hypothesis is stronger than NP hardness, is what we call this exponential time hypothesis, which says that free SAT cannot be solved in like sub-exponential time, okay, in time like faster than 2 to the n, roughly. Okay, so under this assumption, we have even this very strong kind of like inapproximability, okay?
So sets in X time, that puts a lot of things in X time, doesn't it?
Indeed. So that's a motivation for this
It's a
work.
very strong hypothesis. I mean,
It is a strong hypothesis, but as far as we know empirically, it's true, right?
It's possible, but I mean, a lot of people would, they stop short of declaring that NP is a subset of X time.
Right. So, okay. So, you can relax this a little bit, but the minimum that you need to have anything non-trivial here is that you cannot solve SAT in time less than 2 to the square root of n. So you need something stronger than NP hardness, but doesn't have to go all the way up to exponential. This is just to get this nice answer here.
Yeah.
Okay.
Good.
All right. So this is what was known, right? The algorithms and the hardness result. Then now let me tell you what we got a few years ago, and was the beginning of what I'll tell you next. Is that if you look in terms of algorithms, actually you can get the same scaling, right? This some exponent. So it's not a practical algorithm, but shows that it's much easier than this NP hardness result might suggest at first sight, right? So there is we call a quasi-polynomial time algorithm. So it's polynomial both in the dimension of A and dimension of B. So it's better in the error. So this is only good when error is like constant or something, right? And this is both for the Euclidean norm or for the one-way LHC norm, okay? So now, as I said, this two norm is good from some geometric point of view. This one-way LHC norm is more natural from operational point of view, right? And what's intriguing is that this bound, right? Okay, so I say here. So one corollary is that in two norm the problem cannot be NP hard when the error is somewhat large, right? Like polylog, because if it were, we could solve SAT in sub-exponential time, right? So assuming that we cannot, this shows that there is a change in complexity from very small error to kind of error which is a little bit bigger, right? So you have to contrast with this one. Another thing to mention is that, well, first, the same thing is true for the optimization version of the problem, HSEP, but now we cannot do for any M, we have to do for special M. And basically for M, which is one-way LHC, right? For this kind of measurement of matrices, we have this kind of algorithm as well. And now you can compare with this, right? So from this result by these guys, right? That there is no such an algorithm with this running time. Now the thing is that in their result, they can only prove hardness for a slightly bigger class that's called separable. It's almost the same as one-way LHC, but the normalization is different. Okay, so we have like almost, we have like very suggestive algorithms versus hardness results. The function seems to match, but the norms are wrong. Okay, so and this is one of the open questions we'd like to solve in the end. So it really appears there is some suggested evidence that this might be the right complexity for the separability problem, but we don't know yet, right? So we have evidences, and it's really to put them together is an open problem. All right. So what is this algorithm? Okay, so it turns out that this algorithm is not new. It's actually just based on some very useful. When did I start? I lost track of time. Just
1:35.
Okay, thanks. So it turns out that what we do is we apply a well-known algorithm technique to this problem. Okay, and we just find a way to analyze it better. And this is what we call this sum of square hierarchy. Okay, SOS hierarchy, also known as Lasserre hierarchy. Okay, so this problem, HSEP, right? Let's focus on this now. It's easy to analyze. We just maximize over unit vectors and this quadratic function, right? So biquadratic function in the elements. So this is just a polynomial optimization problem under the hypersphere, and the hypersphere are just polynomial constraints again, right? This is just like sum over xi squared equals 1. So whenever we have optimization of a polynomial function over polynomial constraints, we can use this hierarchy that's called S hierarchy that I will show you in the next slide, more details. But basically this hierarchy that is also called Lasserre was also introduced by Parillo independently. What it gives is a sequence of semidefinite programs, right? And these semidefinite programs we can solve efficiently in the dimension of the matrices that approximates increasingly well this function, this number. Okay?
Basically a binary search between the two subspaces. Is that what it is?
No, it's more elaborate. Yeah,
More elaborate.
I'll show you more.
Because there are log step versions of this kind of thing elsewhere in optimization.
Oh, I see. Yeah, no, I think this is something else. Yeah, but
Is it more like hypertorus here instead of hypersphere? Isn't it a product of two hyperspheres instead of?
oh, you're right. Sure. Yeah. It's just right. So you have two hyperspheres indeed. Yeah.
I remember there was a paper by Doherty et al. They came up with an infinite hierarchy of S.
It's just this one. I'll tell you next. Yes.
Okay.
Yes. Good point. Yeah. So it has two properties that are useful. First, there is a k, an integer, which parameterizes the level of the hierarchy that you are. For each k, this is a STP, and the size of the STP is polynomial in the dimension of M. an exponential in k on the levels, okay? And we know that when k goes to infinity, we really converge to the right solution for every m. So if we're willing to wait long enough, we can always get as good approximation as we want. So this is a nice hierarchy because there are all different kinds of SDP hierarchies, like or also linear programming hierarchies like Sherali-Adams and Lovász-Schrieffer and so on.
How quickly does it converge?
That's the question that we address. Yeah, and this is like we know for a few problems. For example, this theorem that I show will come about proving that this converges faster in log n steps, log n levels. Yeah. But yeah, we'll get to that. So this hierarchy that is very interesting because first is the strongest SDP hierarchy that we know. So if we want to try to solve a problem, we should use it, try to use it, and see what it gives. It also has a lot of connections with interesting things like this. There's this sum of square proof system. It's a way of automatizing proofs. I don't know much about it, but it's tightly connected. It's connected to real algebraic geometry and as you see just now to this Hilbert 17th problem. Okay, so let me just show you very briefly what this hierarchy does in a very simple case. So the problem is the following. Suppose we have a polynomial f of x over the reals, and we just want to decide whether this polynomial is positive. Okay, so it's bigger than 0 for all points. Now there is there's a particular class of polynomials for which they are always positive by construction. These are the sum of squares, right? So we say that a polynomial is a sum of square if we can write it as a sum of square of other polynomials, right? Of course, this is always positive, right? Moreover, actually, if I give you f and you don't want to check if it's positive, but you just want to check if it's a sum of squares, this is a SDP, okay? So how is the SDP? Well, so you are given f of x of degree d, and it's a sum of square if and only if there is some PST matrix Q such that we can write f in this form. So we just write a vector z, which are all the monomials, okay, from degree 0 up to degree d over 2. And then we just say these two polynomials are the same. And the same means that we just look at all the coefficients of this one and equate with the coefficients of this one. And now if this is a sum of squares, you can prove that Q must be PST in this representation. So we can just look for a representation of this form with a PSTQ.
It's a pretty simple argument.
Yeah, right? So to check if a polynomial is SOS, that's actually very efficient, right? Right, of course it grows with the degree of exponential with the degree of the polynomial, but for a fixed degree, it's very good. This shouldn't be here, but now it should be here. Okay, so what's this hierarchy? This hierarchy is to try to use this argument to solve this original problem, okay? It turns out that there is no good parameterization for this problem. Actually, to compute this problem, in general, it's NP hard. But there is a way of approximating solutions of this problem using this kind of arguments. And this is exactly this SOS hierarchy. So the level k of the hierarchy is the following for this particular instance. You just take f of x, you multiply by this polynomial, which is of course positive, and you check if this product is sum of squares or not. Okay? This is STP of size n to the order k, right? So for every k, you can solve this STP and see what you get. Now it turns out that this is complete when k goes to infinity. So it turns out that a polynomial is positive if and only if there exists a k for which this is sum of squares. Okay? In other words, every positive polynomial can be written as a rational function of two SOS polynomials. This was a problem, the 17th Hilbert problem, proposed by Hilbert a long time ago and solved by Artin in 25. Okay, so this is goes a long way in mathematics, but the innovation of Lasserre and Parrillo was to observe that you can solve this by STP. Okay, so this gives this hierarchy of STPs. All right, very good. So now, of course, we can apply this to our problem, right? So we have an optimization problem. It's easy to turn into a decision problem. So the maximum of this function is equal to the minimum real number such that this is a positive polynomial, right? It's easy to see. You just put this on the other side. You divide by this to be unit vectors, and you get it. So now we just have to check that this polynomial is positive. And of course, we can apply this hierarchy. This is the k level of the hierarchy, okay? So you have something of this form. All right, so definitely you can use that. But now what I want to do is look at this quantum angle to the problem. Okay, so what I want to do is not consider this derivation of the hierarchy, right? But actually show you how we can think about this hierarchy in a quantum way. Okay, using like quantum states and multipartite states and so on. And this will give, at least in my view, a more natural way of thinking about this hierarchy. And then once we have this view of the hierarchy, we can prove the theorem, which is basically saying that the hierarchy converges faster, okay, than like in exponential time.
Fernando,
Yes.
you say it's NP hard. Is it believed not to be NP?
This thing here?
Yes.
Well, I believe P is different from NP, right? So.
No, but this particular problem is not believed to be inevitable.
Oh yeah, indeed, because it's solved in general. Yes, because you can prove that to solve this problem for every polynomial, it's NP hard in the degree of the polynomial, right? And also in the number of variables.
So when you guess, this K is a priori unpredictable.
Oh, exactly. So if you want to solve this problem in general, in the worst case here, indeed you have to go to K, which is linear in the number of variables, which gives exponential time solutions.
But for each f, there will be such a k.
For each f, there is such a k. But the k might be very big indeed. But now here we are interested in the special polynomial, right? So there is hope that you can do something better, right? Which is, yeah.
So Porrillo started looking at these polynomials
Yes.
as a way of finding the Lyapunov functions.
Right. Yeah, some control theory problem, right? Yeah. I don't know the
And
problem very well.
this is sort of the converse problem in a way, which is, okay, so what functions can you reach with those polynomials?
Right.
I mean, the objective is, pun intended, is to come up with something that actually forces the state down in the usual Lyapunov stability way, right?
Yeah.
And so the question is, how general is that? For how big? The history of this would be interesting.
Yeah. No, there's a
Next
yeah.
time somebody's in Boston, you can ask Porrillo how this came about.
It's true, but it's actually much before Parillo as well, right? So like Shaw, not Shaw from quantum algorithm, but the other Shaw from optimization.
Oh, yeah.
He also was considered this hierarchy a long time ago, and this came from several different communities. They all came to the same, right, to the same algorithm. All right, so now I want to find this quantum way of looking at this hierarchy, okay? And this quantum way will come about considering a very interesting feature of quantum correlations of entanglement, which is the fact that they are not shareable, okay? So let me explain what shareable is. So this is to say that classical correlations are shareable. What I mean, well, suppose you have a separable state, a state of this form. So this is a state between Alice and Bob now, right? Now it turns out that we can find a bigger state between Alice and many Bobs, such that all the correlations between Alice and each one of the Bobs are the same, okay? So how we construct this state? Well, that's the state, right? So we just take the same probability distribution, the same state on Alice, and we take k copies of the state on Bob, right? So this is a state for which all the marginals of A and each one of the P's is the same, and is the original one, right? So in this sense, these correlations between Alice and Bob, they can be freely shared, right, with an arbitrary number of Bobs. So this is the motivation for making this definition, which is that a state, a quantum state rho AP, is k extendable if we can find a bigger state of Alice and k Bobs, such that for all j from 1 to k, if you take the state, we take the partial trace over all the Bobs except the jth one, we recover the original state, right? So a state is k extendable if there is a state of this form for which all these reductions A and B3 or A and B4, they are all equal to the original states, okay? So the correlations between Alice and Bob can be shared to k Bobs in this case. Now the interesting thing is that entanglement is monogamous in a sense, right? So there's this called monogamy of entanglement that we talk a lot about in quantum cryptography, for example. But here really just gives another characterization of entangled states, right? So it turns out that a state is separable if and only if this state is k extendable for all k, okay? So if it's separable, we know it's extendable for all k. I just show you how to construct the extension. But it turns out that this is necessarily sufficient for being entangled. If it's entangled, for some k, it has to fail, okay? So you cannot like share these correlations arbitrarily. So this gives a way of setting up an algorithm for the problem, right? So we are interested in characterizing this set, the set of infinitely extendable states. And what we do, we can just, well, come up with a hierarchy, right? We say, okay, so let's test if the state is too extendable. If it's not, we know it's entangled. If it is, then we test if it's free extendable. If it's not, we know it's entangled. If it is free extendable, we have to go to for extendable, and so on, right? So we have this sequence of tests. And to see how well this performs as like computationally, we have to ask these two questions, right? So first, how close to a separable state rho AB is if there is a k extension, right? We know if for every k there is a k extension, it's separable. But is there some approximate version? This is one problem. The second problem is how long does it take to check if a k extension exists or not, right?
It's not quite entangled. It's just the size of the harem is bound.
That's right.
Is bounded.
That's right. Yeah.
Really?
That's true. And if you're like maximally entangled to someone, then you're monogamous, right? Yes. Yeah. Only then. All right. So now what's this that Matti already mentioned? This was this was discovered 13 years ago by Doherty, Parillo. That was one of the guys who introduced the hierarchy, and Spedalieri. They just saw, well, this problem. This is for the 8-SEP version, right? So, but you have the wiki membership as well. This problem of computing this is equivalent to, of course, you can write the sum of square hierarchy for this problem, but this is also equivalent just to optimization over k extendable states, okay? So like when you go to higher extensions, what really you're doing is to go to higher levels of Lasserre hierarchy, plus some other tests. That's called PPT tests, but these won't play a role in what will follow. But so what's the way of writing this STP? Well, we just maximize trace. M is the input of the problem over a matrices pi, such that there exists a big PSD matrix of units trace for which all the reductions between A and Bj equals to pi. Okay. So basically, we're just optimizing the linear functional over the set of k extendable states. Now we add something more that's not only there are k extendables, but if you take the partial transpose over some set of the B's, this is still a valid density matrix. Okay. Don't worry about this constraint. This is just to recover Lasserre, but we don't know how to use this. This is another open question. So basically, you can think that Lasserre is really just, instead of optimizing over separable states, over this biquadratic optimization problem, you relax over some set of bigger quantum states, which gives a proxy to separable states. Okay, so this is what's happening here.
Sorry, but is it like, I remember back then many people try to show that this is actually finite in the sense that given a state there will always be a k.
That's true. And it's true.
It was unknown back then. Is it now solved that? I don't want to steal your thunder, but is that?
Well, to tell you the truth, this was solved even before they did this, because there were some works that are mentioned on mathematical physics giving the answer.
I see.
But right, when they were working on that, I don't know what they knew.
For each
entangled state, you can find a k for which you solve, but this k might be, of course, very big, right? So, all right. So this solves this question, right? So, how long does it take to check if a k extension exists? Well, it takes time, local dimension to the power of k, roughly, right? Because we have a STP for it.
Oh no, I didn't mean extension. I mean testing whether an entanglement witness exists. It's a different question, right?
It's very close to this, like because.
I mean, it's separating hyperplane.
That's right, but once. Right, so this is basically optimization over the separating hyperplane, right? So if you solve the weak membership version of this problem, if you get an infeasible solution, meaning that it's entangled, right? Then if you go to the dual, this will give the hyperplane, which is the entangled witness. Okay. All right. So now the question really is how close we are from separable, right? If I say this k extendable, right? So how fast this hierarchy works. And there's a lot of work, like starting. Well, I didn't put the reference here, but starting from paper by like Reinhard Werner in 88, I think, studying these bounds that we call Diffie-Netzi theorems. Okay, that they are useful for several things. But now here I don't want to explain what they are. I just want to show this kind of bound that was known before. It's known that when k grows, the set of k extendable states, right? If rho is a k extendable state, it gets closer and closer to separable. But the bound wasn't so useful for algorithms because it was, it was very as a quadratic as the square of the local dimension. So now if you look at the k that you need k is the level of the hierarchy, right? To get a good approximation, this k has to be proportional to the dimension. And because the STP is exponential in k, this only gives exponential time algorithms, right? So this shows that the hierarchy is complete, but doesn't give something in terms of algorithms. And actually, this, it turns out they cannot improve on that. There are examples which almost saturate the inequality. So this dimension, if you want one norm, which is this nice norm that I mentioned, if you really want in one norm, there is not much you can do here. So now, this theorem that I mentioned before comes from information theory result, result in quantum information theory, which is the following: that if a state is k extendable, but now we don't care about trace norm, but we allow one-way LHC norm or two norm, then we have an exponential improvement in the performance of the disfinity, right? It doesn't go with dimension, local dimension, but it goes with log of local dimension, okay? And once we put this into the problem, we get exactly this running time that I mentioned, okay? So this is the main result behind this initial theorem that I show you. It's really that how well k extendable states approximate separable states goes with the number of qubits of the states and not with the dimension. If you use these two norms, if you use one norm, it's much worse, right? So there is this huge difference between the norms that you use. And if you want something more efficient, you have to use these weaker norms. All right. So, this is just, I guess, right? So if we use this number of rounds of SOS, right, we know that we can solve, put in here, we know we can solve the problem with error epsilon. And the size of the STP is just the size of the extension. And the size of the extension, the dimension of the extension is dimension of A times dimension of B to the power of K, because the state has one A parts and K B parts, right? So putting the numbers, we get exactly this running time. All right, so I guess, let me see. I'm running out of time, and I want to mention some applications of this result to purely classical problems, which was the question Matt asked. So I had a sketch of the proof. So the proof basically is to use quantum information theory ideas. Okay, so like you use mutual information and you use chain rules and so on. And then, but I will skip that because I don't have much time. So this was just to show how you can prove it using some quantum information ideas. And let me get to these classical problems then. Okay, to finish the talk. So now it turns out that this HSEP, of course, is useful for solving separability, which is this problem we care about in quantum. But it's also equivalent to a lot of other problems that people consider elsewhere. And I just want to mention these connections and what we can learn about these problems, right? So what I just show you is that this Lasserre hierarchy, this sum of square hierarchy, there's a way to think about it in quantum terms, right? You can think in terms of quantum states and extensions, and right? And I didn't show you, but once we have this way, we can use quantum information tools to bound how fast it works, right? So now it's just natural to apply these bounds that we have to other problems, like to classical optimization problems, right? And see what it gives. So this is what I want to show you. So we don't have like a killer result yet, but we have some, I think, some suggestive evidence that something useful might come out of it. And I want to show you now. So there are several like equivalents which are pretty easy to show and won't be the focus. Like, one thing is equivalent to compute the injective norm of tensors. Right? The injective norm is just this generalization of the maximum eigenvalue or singular value. For other problems in quantum information, we can connect them to like compute the minimum output entropy of a quantum channel in infinity norm at least is equivalent to HSEP, or computing the optimal acceptance probability of quantum Merlin-Arthur proofs with two independent provers. It's the same as HSEP. So there's a lot of other problems in quantum information that are equivalent. Now a problem that I want to focus is this problem of computing the 2 to 4 norm of a projector or of a matrix in general. So this is just some hypercontractive norm, right? So the definition is that we maximize over unit vectors the 4 norm of p times x, okay, over x of unit vector. And now it turns out that you can relate these two things. So you can prove that if P is any matrix, actually, it doesn't have to be a projector. The 2 to 4 norm of this matrix equals to HSEP for M of this form, okay? So K is just the computational basis, and this is what you get. So if you can compute HSEP in general, we can compute this for all P's. Okay, so why is that? Well, it's very simple. So let me just go really quick. if you have a matrix A, right? So you want to compute the 2 to 4 norm of A. I was calling P before. So this is the computational basis, whatever you want. And here is vectors, right? So you can always write A in this form. You can always find vectors A of I for which capital A can be written in this form. Now the easy direction, right? Okay, so now, of course, by this identity, which is very easy to verify, you see that if you can compute HSEP, you can compute 2 to 4 norm as well, right? Just because this 2 to 4 norm is a particular case of HSEP, right? So, and this is just the math. Now, actually, the other way is also true, which is the more interesting direction. If you can compute, or at least like if you can approximate 2 to 4 norm, then you can approximate HSEP as well. Okay, so it turns out that they have similar complexity, these two problems. And this use some quantum argument as well that I will just skip. If you want, you can ask me later. So we use some ideas from quantum information to prove that. So now why this 2 to 4 norm is interesting? Well, for one thing, because this is a hypercontractive norm, right? So this appears like, in Markov chain, if you want to prove convergence time of the Markov chain, you want to bound this 2 to 4 norm. But more really because it's connected to two other problems that I just state what they are, which are like, very important problems in current research in combinatorial optimization, which are problems that we don't understand the complexity and we don't understand what we can do in terms of algorithms, but that we like to understand. And maybe this connection tells us something. So let me just tell you what the problems are if you don't know. One is related to this unique games conjecture, okay? So before I tell you what the conjecture, let me tell you what a unique game problem is. This is the problem. This is the following. Oh, no, this is the conjecture already. Okay, so this tells you that suppose you have a system of equations of this form. Just two variables per equation, xi plus xj equals c mod k. Okay, well, these are like two integers. So it's solving a linear system of equations with two variables over some finite field. Now this conjecture tells us that this is a very hard problem, actually, even to estimate. It tells us that it's NP hard to tell whether more than 1 minus epsilon fraction of the constraints are satisfiable, meaning that there is a assignment for the x which satisfies 1 minus epsilon fraction of these equations. Or if you cannot satisfy even an epsilon fraction of them, okay? So you promise that either almost all of them are satisfiable or almost none of them are satisfiable, and you want to decide which is the case. And the conjecture is that this is an NP hard problem. Okay, so this is just a problem. Of course, you can make this conjecture. Now, yes.
Unique game. What
unique because the constraints. This is a constraint satisfaction problem of arity 2, and it's unique in the sense that given one assignment for this variable, there is a unique assignment for the other variable which satisfies the constraint, and vice versa, right? So if you choose xi say equals 1, there is only one choice for xj that would satisfy this constraint, and vice versa.
Unique solutions.
It's not a unique solution. It's like is a unique choice for one of the variables in a constraint given the choice of the other one.
Right.
So is
given something about k.
Sorry?
Unique strategy.
Right. Yeah.
Yeah, I mean, given something about k.
Okay, C and K are just parameters of the problem, right? So you're fixed from the beginning.
Yeah,
Just besides the problem.
For arbitrary k, then clearly that's right.
The conjecture is that for any constant C and K, this is true.
Yeah. Does it have anything to do with the number of unknowns? Suppose I give you.
So you don't know any of the x's, right? You have n x's, n variables, and you don't know what they are.
Okay.
Right,
so,
and you have to.
So there's n of those, right?
Yeah. Yeah, the problem scales with n, the number of variables.
Yeah,
exactly.
So if k is very small compared to n, then I think this might behave like SAT, like KSAT, in that if you have too many constraints, then there's no solution. And if you don't have very many
sure, yeah, right.
then it's easy. And it's only for critical k.
Right.
K is some function of n to make this hard, I think, is the point.
So what I say is true, but it's not in terms of k, I think. Maybe also in terms of k, but in terms of how many equalities you have, right?
Which is n, right?
You have n variables and you have other n equalities, right? Constraints. Yeah, and then of course there is some ratio for which is the hardest. Yeah. All right. So now why people care about this problem, right? Why this is an important problem? Well, for many reasons, but one of the reasons is that Haravendra proved that if the unique games conjecture is true, then if you look at the second level of this SOS hierarchy, okay, this is the best possible algorithm, gives the best possible approximation for any constraint satisfaction problem. Okay, so this constraint satisfaction problem is a huge class of combinatorial optimization problems. If we can prove that, we really understand everything we can do in terms of algorithms here, right? We just use Lasserre, second level, we get the best approximation possible. And to try to get any approximation better than that, it's NP-hard. Okay, so it's really a meta problem for which, if you understand it well, we can understand a lot of other problems. And you can see this as just a major barrier in our current knowledge of algorithms, right, for these problems. Now, this is not really a conjecture that everyone knows is true. In fact, like, it really could go either way, okay? It's really like where our knowledge goes. And one of the ways to see that is that actually some years ago, Aurora, Barak, and Steuer found a sub-exponential time algorithm for the problem. Okay, so given any epsilon, you can solve this in time exponential and to the other epsilon, right? So, of course, it's not really efficient, but it's not like SAT, right, which appears to be this exponential lower bound. All right, so this is one problem. The other problem, okay, maybe I'll just mention that. Sorry for introducing so many problems at the end. I just want to show what is this implications. So this is a problem in graph theory, which is very tightly connected to unique games. Okay, so we believe they are equivalent, but there's some caveats. So this is the problem of telling given a graph, right? So we have a graph and we have two parameters. We want to understand whether for all small subsets of vertices of the graph, they expand really well, all the vertices leave them, or if all the vertices stay inside them, they expand really poorly. So the conjectures say that it's NP-hard to tell whether for a graph with vertex set V and edge set E, the expansion, this is the definition of expansion, it's just the probability that an edge from M leaves M. Whether the expansion of all small sets is smaller than epsilon. A small set just means a region of size like subvolume, okay? So small constant delta times the total volume. So we care about small regions. And we want to know whether there is this one region which is really non-expanding, right? Everything stays inside. Or if for all small regions, they are almost completely expanding. Everyone leaves, right? All the edges leave them, like almost all of them. And this is the small set expansion conjecture, okay? Again, it's conjecture to be NP-hard. Now, why I tell you all these problems? Well, because we have these equivalence, or like approximate equivalence in some cases. Okay, all these problems, they appear to be like the same complexity, okay? So there are a lot of like caveats here and technicalities that I'm glossing over. So this, in one direction is known to be true, in the other direction is conjecture to be true. This is what I mentioned at the end, right? Again, there's some caveats in the conversion of errors, but that's roughly true. And this is what we prove in this paper, right? That's connecting HSEP to 2 to 4 that I just showed you, and 2 to 4 to small set expansion, okay? So now, given these connections, and given that we have some new results about like algorithms for this guy, and that I mentioned also hardness for this guy, we can try to convert them, right? And this is what we did. That's the last slide. Let me just mention the results. So this is what we could prove using these quantum ideas for Lasserre hierarchy. This is what it gives for 2 to 4 norm, for example. Given a matrix n by n, we can compute in this number of rounds of sum of squares, so logarithmic in the size of the matrix, additive approximation to the 2 to 4 norm, okay, where the error is this one. So this is a natural error because you can always prove that the 2 to 4 norm is smaller than this error, okay? So you just show that there is this natural upper bound, and you show that you can have this kind of additive approximation. So it's not clear if this is good for anything, right? So, but actually,
log of epsilon to the minus 3 is kind of that epsilon to the minus 3 out in front is looms large.
Oh, it's epsilon to the minus 2, but you'll be large. Oh. Yeah. No, sorry, it's a mistake. It's a typo. My typo. Yeah.
Okay.
But you're right. So
that's better.
Well, yeah, but of course, it's very costly, right? Because the running time will be n to the other n over epsilon square, right? Which is exactly what we saw before, right? So 2 to the log square n. So so you see why these were the kind of bounds that we had for the quantum problem, right? So if we convert to this problem, we get this. This just comes from the normalization of like one-way LCC measurements, for example. I'm skipping over the details. Now, if you apply this, actually a similar bound for 2 to p norms, you can recover the sub-exponential time algorithm that I mentioned before, okay, which is the state of the art for small set expansion. So So we don't have new algorithm results using the quantum ideas, but at least we can recover the best thing that people know classically, which is a sub-exponential time algorithm for a small set expansion. Okay, it just gives an alternative analysis for the algorithm. Now, it also leads to new open problems, okay, which I think are interesting. So if we could improve this quantum analysis in several ways, this would lead to new classical algorithms. And I think that's something interesting. So, for example, if an improvement in the bounds, right? So I showed this definite bound, it was an additive error. If you could have a multiplicative error, then you could solve small set expansion in quasi-polynomial time. Okay, so this would be strong evidence against unique games, right? So they could not be NP-hard with this running time, unless something very weird happens. We can also
unless you get famous, right?
that's right. Yeah. But,
Would it also give better approximation algorithms for, say, max cut?
no, because that's a sad thing about unique games conjecture. If it's true, we understand everything. If it's not true, then all these equivalents, they are lost. So you have to work case by case. So
On the no-go side.
that's right. Yeah. So there are also quantum arguments for hardness results. If we could improve on those, we would also get this kind of lower bound for unique games, right? Which seems to match. So so improvement is something that I didn't mention. So now the point is that this improvement can be cast at these open problems in quantum information theory, right? That we don't understand yet, and we would like to understand. So one possible strategy for trying to solve unique games conjecture is just to learn more about quantum information theory, right? So there is this new bridge, and I think it's worth exploring more and see what we can get in terms for these classical algorithms, considering this new quantum view that we have. So that's all. So what I told you is just that this. I hope the message was this SOS is a very useful algorithmic tool for problems in quantum information. I give you just one application. There are many more in quantum information itself. And I show in particular how we can get this quasi-polynomial algorithm for deciding entanglement from this hierarchy. What was unexpected to us, and I think it's a nice bonus, is that conversely, quantum information theory is also a useful theoretical tool to understand the performance of this hierarchy, right? So it gives new insights into this hierarchy. And I show you some connections to 2-to-4 norm and small set expansion with quantum separability. And use this new connection, this gives potentially a new approach to resolve this unique games conjecture, right? So, of course, it's a very hard conjecture. I don't claim we are close to solving it. There's a lot of barriers that might be very, very hard. But I think it's something new to think about, which is interesting. So that's all. Thanks.
Questions for Fernando?
So in some sense, Schur's algorithm entangles everything
Right.
and achieves a very nice speed up as a result of that. It seems like this suggests that if you had more fancier ways of generating entangled states, then you might be able to achieve exponential speedups if this sum of squares approach lets you get at the decomposition. I mean,
you mean at the decomposition of the separable state?
yeah. Well, the approximation of the
Uh-huh.
the decomposition of the separable states.
Yeah, well, I guess a different regime here. So here really we care about complexity in terms of dimension of the states, right?
Sure.
Of course, if you have an n-qubit system, the dimension is already exponential in the number of particles, right? So,
Right.
and this is complex. There is nothing we can do about, right? So I think this is one level below it, right? So this is really even for very small quantum states, already it's very hard to decide separability for them, right? There is the exponential growth of the dimension with the number of particles, but even if the number of particles is quite small, this already becomes a hard problem, right? So,
Yeah, I'm just thinking about, for example, quantum Monte Carlo.
yeah,
Let's suppose I have I want to speed up the rate at which I can compute
yes,
let's say the occupancy of the states after a simulation. If I can use entanglement to make up for randomization in the Monte Carlo process, so I entangle things in such a way that I superimpose the things that need to be superimposed, the things that really are additive,
Right.
and not the things that aren't, then I might be able to design an algorithm which would use entanglement more surgically over those all those paths. If you know what I'm saying?
Yeah. Well, I guess no. Yeah.
Yeah.
Okay.
So as a, I mean, yeah, I'm just. I mean, the problem is how do you do that, or how do you describe the entanglement you want?
Right.
That will result in the right answer. So this is interesting from that point of view.
I see. Right.
I mean, you aren't going to get anything that's exponentially good unless you entangle, I think. I don't know how in the world you're going to do it if you just, you know.
Yeah, for some problems, yes, if you don't have a very entangled.
Well, DQC1 provides a natural counterexample to this, where you can have very small amounts of entanglement and apparent exponential speedups.
Right. That's true.
Yeah,
of course, it depends how you
yeah.
count this entanglement, right?
Yeah,
so
I'm not-
how you quantify it. So,
Absolutely.
But, yeah.
What I'm saying is something a lot weaker than that, and that is if there's no entanglement, then it's hard to get an exponential speed up. That's all. Not small amount, but, I mean, you might not need much as long as,
There's no entanglement, aren't you classical?
Sorry?
There's no entanglement, aren't you classical?
Yeah,
Well, by definition.
yeah, but it's true, but it's actually an open problem. So suppose you have a quantum computation
Yeah.
for which your promise that, but with mixed states, right? With mixed states. With pure states. Okay,
Pure
with,
states.
then it's clear. Yeah.
Okay, fine.
It's
Yeah.
clear.
Just
With
making
mixed
sure.
states,
Yeah.
we don't know how to simulate. If you have this
Okay.
problem that you always have separable states, fully separable states, we don't know a way
mixed states, right?
Okay.
of simulating it.
Yeah.
You have equivalence between 5 programs.
Yeah.
So it looks like there is a I don't know how natural, a complexity class. The people try to develop reduction theory, complete problems.
Yeah.
Right. So because this unique games is this important problem, people thought about that, but
Those arrows aren't all solid, of course, right?
yeah. So this and that was the reason for introducing this problem, small set expansion. This is a problem they believe is really reducible to unique games. One way is proved, the other way is conjecture. There is strong evidence, but there is no proof. Now, unique games, we know that if unique games are hard, a lot of other problems are hard as well. That's why it's a very useful one. Okay, so it's like to prove unique games hardness.
It's space, yeah.
Right. So yeah, unique games is a class
You
that
reduce everything to UG in some sense.
That's right, but in one direction only. That's the problem, right? So, like people have tried to work out, for example, max cuts. They really tried to prove that max cut was equivalent to unique games, but they couldn't do it. So, it's more like, we know a lot of problems which are unique games hard, which are not known to be NP hard, but we don't know if they're equivalent to unique games. Right.
It's a
But,
good place to look for a quantum algorithm, actually.
yeah, if you could get a quantum algorithm for unique games, would be
Yeah, but
great.
I mean,
Yeah, because you disprove it's NP hard.
It's not
but,
known if it's an NP, then
That's true. Yeah, and you'll be
it's fertile ground.
So a separate question, if all these optimization problems are equivalent to some question about whether a quantum state is separable or not, is there any hope for maybe some quantum algorithm that at least does like low levels of the Lasserre hierarchy faster or something like that than a classical algorithm?
I never thought about that, but it would be nice. Yeah, but maybe, yeah, but I don't know. I cannot think how you could search for this symmetric extension by a quantum algorithm, right? But it's, I guess because it seems to be intermediate complexity, there is some hope that it can do something there. I don't know. It's a good question, but I never thought about it. I don't know.
You mentioned a quantity called the injective norm of a
Yeah.
3 tensor.
Yes.
Can you explain what that is? Is that related to the rank of a 3 tensor or so?
It's something different from the rank here.
What is it? Can you
it's just
explain
this,
the intuitive way to understand?
Well, it's really just it's just a generalization of of
It's kinda like
singular
the big-
value, right? So
It's kind of like the biggest singular value of a tensor.
exactly, yeah, right? Because if you just have 2, then it's exactly a singular value, right? So, but now you have more indices, so you just. But now you want some geometric interpretation like singular value. Then I don't
I'd like to know
Then I don't know.
if that has any implication of the most famous 3 tensor that there is, right? The matrix multiplication 3 tensor. Does it say anything about the asymptotic?
But this is connected to the tensor rank, right? This
Yes.
matrix multiplication, right?
Which is unknown.
Right.
As far as I know.
That's right.
For
That's
the
right.
for the
So
matrix
there might be, and I'm not aware of. But this is not the same as tensor rank, but I don't know if there's relations. I don't. There could be. Yeah. I don't.
Recently, there were improvements on that rank, like over Coppersmith, Vinogradov, but
Right.
I'm not sure if they followed optimization approaches at all. I just don't know how they work.
Even this Cooper-Smith.
They brought down the exponent a little bit.
That's right. Very recently, right? Like.
Maybe one or two years ago.
Right. But this was by this Virginia Williamson, right?
I don't know.
Someone. Yeah. Right. Yeah. I don't know what they do in this
with
book.
this? Okay.
I don't know. Yeah.
Any other questions? Otherwise, let's thank Fernando.
Thank you.